Okay, hello everyone and welcome back to your YouTube channel. And welcome to this very interesting video today. We have a video regarding a numerical example for kinetic energy calculation and acceleration in a synchronous generator. What we are doing here is using a MATLAB live script to show you some calculations, basic calculations regarding kinetic energy and the acceleration in this beautiful synchronous machine. Let's start here. Consider a 60 Hz 4-pole synchronous generator, rate 85 MVA. This is the apparent power, the rate apparent power, and 13.2 kV. That is the rate voltage. This is RMS line-to-line voltage. And this machine has a inertia constant, rotational inertia constant H of 6.42 megajoules per MVA. Megajoule per MVA is equal to megawatt seconds per MVA. Then we have here two very simple questions. Calculate the kinetic energy in megajoules stored in the rotor at synchronous speed. And the second question here is calculate the angular acceleration using this Greek letter alpha if the electrical power developed is 60 megawatt when the input less the rotational losses is 120,000 horsepower. Wow, that is a lot. Now, we want the results in radians per square second, electrical degree per square second, and RPM per second. Well, here I have included this remark, but this is for my YouTube user, because I know that all my students, they remember this conversion over here. I mean, 1 horsepower is equal to 746 watt. That is something that everybody must know, okay? Well, let's start the solution. The first step here is the input data, frequency 60 Hz, rate apparent power 85 MVA, 4 poles, and the rotational inertia constant is 6.42 megajoules per MVA. The electrical power that is delivered at the stator of the synchronous machine is 60 megawatts. And we have here the mechanical power, in this case, 120,000 horsepower, okay? We define here a small constant to provide the conversion. In this case, we are converting from horsepower to megawatts, okay? Well, it's very simple. The first step, we will convert this horsepower into megawatts. For that reason, it's extremely simple. What we need to use is multiply the 120,000 horsepower by this conversion that we have over here. And voila, we have that the mechanical power is 89.52 megawatts. Okay? That is the mechanical power that we are applying on the shaft of this beautiful synchronous machine, okay? Okay, now what we need to do is calculate the kinetic energy stored in the rotor of this machine when the rotor is rotating at synchronous speed. To do that, all my students, they know, they are extremely clever, they know that the kinetic energy is related to the rotational inertia H. The definition of rotational inertia is extremely simple. It's the ratio between the kinetic energy and the apparent rate power. And from there, we can extract here the kinetic energy. In this case, the kinetic energy in megajoules is equal to the rotational inertia in megajoule per MVA multiplied by the rate apparent power. Now it's just question of applying the numbers, and here 6.42 megawatt second per MVA multiplied by 85 MVA. We obtain that the kinetic energy, in this very specific case, the kinetic energy stored in the rotor of this machine is basically 545.7 megajoules, okay? Now the next step is calculating the accelerating power. In this case, we have the case of a machine where the mechanical power is larger than the electrical power that we are receiving at the stator of this machine. Sorry. As a consequence, the difference between the mechanical power and the electrical power, that difference is what we call the accelerating power. In this very specific case, the numerical values, we have a mechanical power of 89.52 and we have electrical power of 60. The difference between them, you can see over here, the accelerating power 29.52. Next step, I will show you something very important. And the student must understand that the machine, of course, have different references. The magnetic field created by the stator is rotating at the synchronous speed. And to be honest, that synchronous speed is 2 pi f. And in this case, the rotational speed is in electrical radians per second. However, the rotor, you must remember that between the stator and the rotor, we have a conversion related with the number of poles. And in this case, the mechanical rotational speed is related with the electrical rotational speed by a single conversion related with the number of poles. In this case, we multiply by 2 and divide by p, and p represent the number of poles in this machine. Now what I am doing is calculating the rotational speed. Here at the top you can see the electrical, here at the bottom you can see the mechanical synchronous speed. And in this case we are using radian, electrical radians per second, 376.99, or the equivalent to 3,600 RPM. And from the mechanical side, you can see here that is 188.49 mechanical radians per second, or the equivalent 1,800 RPM. Okay, you must be careful here for the rotational speed in RPM. We are using the Greek letter. This is the Greek letter eta. It's not the letter N. This is a Greek letter, is the lowercase letter eta, okay? Now, again, what I want to show you in this exercise is extremely simple, but I need that you understand that depending on the units that you use, you can get different inertia constant M. In this case, M, here I am showing two different equations. In one of them, I use here at the denominator the rotational speed in radians per second, and as a consequence, M will have a different value than the one that you obtain if you use electrical degrees per second. And here, in this example, what I want to show you is, here we have the inertia constant using mechanical radians. In this case, is 5.79 megajoules per second per mechanical radians, and below you can find here the inertia constant in the units of megajoule seconds per electrical degree. Now the next step is using the Sling equation. The Sling equation says that m, the inertia constant, multiplied by the second derivative of the angle delta, is equal to the accelerating power. In other words, m multiplied by the acceleration alpha is equal to the accelerating power. From here, it's very simple to extract alpha. And in this case, alpha will be the accelerating power divided by the inertia constant, but we need to be very careful about the units. If we want the results in electrical degree, of course, we need to use m, the inertia constant, based on megajoule seconds per electrical degree. And that is what I am doing here. What I am doing here is calculating the rotational acceleration alpha in units of electrical degree per square second, and the numerical value is 584.23. Next step, I need to show the results in radians per second, square seconds. And to do that is very simple because it's just a unit conversion. All my students know that we need to multiply by 2 pi radians and divide by 360 degree, and we obtain here the acceleration alpha equal to 10.19 radian per square second. Then we convert this acceleration from electrical degree per square second to mechanical degree per square second. And to do so, what we need to do is use the number of poles. To be honest, it's extremely simple. Multiply by 2, divide by the number of poles P. And in this case, alpha is equal to 292.11 mechanical degree per square second. Finally, but not the end, we will present the results now in this very interesting unit, and this is RPM per square second. And that is extremely simple because alpha will be the mechanical degree per square second multiplied by F and divided by 360. And we obtain here that alpha, the acceleration, it will be equal to 48.68 RPM per square second. What I want to show you is that, well, we finished this problem because we presented the kinetic energy and we calculate the angular acceleration in the different units that we were asked for. And that is the end of this amazing video today. Well, if you enjoyed this video, please subscribe to the YouTube channel, or if you have any question, leave the comment below. I will be extremely happy to answer. And thank you very much for watching, and I will see you at the next one. Bye now.